Gradient descent is an optimization algorithm that is used by other machine learning algorithms to find their optimal parameters. For example, algorithms like linear regression, logistic regression, and neural networks use gradient descent in the backend to find their respective parameters. In case of linear and logistic regression, we call the parameters as coefficients, whereas in neural networks, we call them as weights. Let's take the case of linear regression. We have seen that in linear regression, we are trying to find a continuous y variable as a function of all the other x variables as an input. So we have the alpha, which is the intercept, and we have the respective coefficients of each of the x's. In linear regression, our objective is to find the alpha and the betas, correct? If you take these terms alone, excluding the error, this is the predicted value of our y variable. The role that gradient descent plays here is it finds the optimal values of the alpha, beta 1, beta 2, and how many ever betas are present. It finds their optimal value to make the y hat as close to the y. That is the objective. Now, imagine if we were to do it on our own. Suppose if you are to determine what is going to be the optimal alpha and beta value, how would you naturally do it? What is the worst or the naive way of finding the alpha and the betas? A very crude way is to try out all possible values of the alpha and the beta parameters. For all possible values, we will predict the corresponding y hat values. Y hat is the predicted value. That is one approach. Second approach is a smarter approach, that is the gradient descent we will discuss now. Besides these, there are other approaches as well. But gradient descent is an algorithm that can be generalized to many other algorithms as well. Now let's understand the problem with the first approach. Imagine you have a simple equation. Your y hat value is nothing but alpha plus just one beta we will have and x1 plus error. The error term will not be there. So this is just the predicted value. Now suppose alpha has say 10,000 possible values. Likewise beta 1 also has 10,000 possible values. And if you want to try out all combinations of alpha and beta, you have 10,000 multiplied by 10,000 possible combinations. If you have to add just one more beta, if you have beta 2 in the term, you have one another set of 10,000. Likewise, as you increase more variables, the number of possible combinations that you have to try out increases exponentially, and that is not possible to scale also. So here gradient descent offers a much better approach that will help you to search the optimal values of alpha and beta in the right direction. Instead of searching all over the place, what it does is it computes the y hat in every iteration, and for each y hat there will be a corresponding cost function. In case of linear regression, we have seen this cost function to be the mean squared error or the sum of squared errors, right? Likewise, in logistic regression, there is something called logistic loss, also called as negative log loss. So gradient descent changes the parameter value. Suppose let's imagine we have just one parameter. I'm calling it as beta 1. By checking for various values of the parameters, if there is another beta, there will be another axis along this direction. If there's another beta, there will be another subsequent axis. But let's not consider these for now. Let's make it simple. Let's try with just one parameter for now, and for each parameter there will be a corresponding predicted value of y. For one particular value of beta 1 there will be a corresponding y hat. Another beta 1 plus 1, a different value, there will be a different value of y hat I plus 1, right? So this y, for each value of y hat, we know the actual value of y correspondingly, right? We compare the actual value of y with the corresponding predicted value, and there will be a corresponding cost function we can compute. In case of linear regression, we saw that mean squared error is the cost function. So you can compute the mean squared error using y hat and y. and plot the corresponding cost functions on this chart. So that cost function I'm having on the y-axis. So for one particular value of beta 1, say this is the cost function. After this, we update beta 1 in such a way that the cost function keeps reducing, and after reaching a minimum, if you keep on increasing the beta, the cost function keeps increasing again. So this forms a convex sort of a function. We call this as a convex function. Why? Because if you connect any 2 points in this curve, this is the profile of the cost function itself. If you connect any 2 points, it will not be intersected by any other point in the curve. If you connect these 2 points, or even these 2 points, any 2 points you take in the curve, it will not be intersected by any other point. These type of functions is called convex function. And most cost functions you will encounter in machine learning algorithms, most of them are convex functions. So the gradient descent algorithm updates the beta in a certain fashion that it progressively learns to stop near or identify the near minimal value of the cost function. That's what gradient descent algorithms helps us. And it tries to learn this with a minimum or much lower number of iterations compared to a naive approach. That's what gradient descent helps us. In fact, how fast the gradient descent function learns is dependent on the user. There's a particular parameter called the learning rate. The learning rate ranges between the value of 0 to 1, but typically it is taken a value of 0.01, 0.05, 0.1. It lies in the lower region. By adjusting this learning rate, you can control how fast the gradient descent algorithm learns. A higher value of learning rate, that is towards 0.05 or even 0.1, it makes larger leaps, right? But if the learning rate is too high, it can jump past the minima value and go to the other side of the equation. So you need to control how big or how good the learning rate is. So you need to control the learning rate appropriately for the gradient descent algorithm to converge correctly.